Do you remember back in Module 8 when we were working all of those roller coaster problems and where we were talking about, you've got the roller coaster car up at the top and then it goes down here and then it goes back up to here and how fast is it going when it gets to the top of the second hill? And all of those were basically conservation of energy problems. You had so much potential energy, which was converted to kinetic energy, which then when it went back up had more potential energy. And so it was a continual game of flipping those energies back and forth from kinetic to potential, back to kinetic, back to potential again. The problems that we're going to be working now should look very, very similar to those types of problems. The only difference now is that in place of having roller coasters, now we have particles in electric fields. And so the potential energy is calculated by the electric potential of the particle within that particular field. So I'm going to work through example 14.3 and show you how this works. So example 14.3 says a freely moving negative 15.1 millicoulomb charged particle, and it gives us the mass, is placed 13 centimeters from a fixed negative 2.0 coulomb charge. So let's get the diagram down there first. So my fixed charge is a negative 2.0 coulombs. It is negative, and then I have it starts out 13 centimeters away. And so if it starts here, I'm going to go ahead and change it to meters because I know I'm going to have to need it in meters anyway. So there's my movable charge at 13 centimeters away, and it is, let us see, it's negative 15.1 millicoulombs. Now, notice that this is coulombs and this is millicoulombs, so we'll have to do some conversion here in a minute, okay? It tells me that the mass of this is 2.34 kilograms. So I'm going to need that information here in a little while, so I'll go ahead and put it up there. It says the particle starts at rest. So if it starts at rest, that means its initial velocity is 0, right? It starts at rest. At what speed will it be moving when it is 95 centimeters away from the fixed charge? So let's stop and think here in a second. This is negative, this is negative. What direction does it naturally move? Well, like charges repel each other, so it's naturally going to move away from that, and that is exactly what's happening. It's going to end up at a spot over here, and it wants to know how fast it's going when it's 95 centimeters or 0.95 meters away from this charge, okay? So I want to know when it gets out here, what is its final velocity going to be? All right, so that's the problem. That's how we set it up. And we know that the total energy has to be equal to the potential energy plus the kinetic energy at all points, just like we did back in Module 8 with the roller coaster problems. So since the initial velocity here is 0, what that means is that everything it has at this point is all going to be potential energy. So the total energy here, since it is not moving, is going to be the same as the electric potential. So the other thing that I'm going to be able to calculate then is I can calculate the electric potential at this point and the electric potential at this point. So that's what I'm going to have to do. Again, because I already know that the change in potential energy is the same as Q times the change in the electric potential. So I'm going to have to find change in electric potential first. So the initial electric potential for this, remember that we do that by finding KQ over R. So K is 9.0 times 10 to the 9th Newton meters squared per coulomb squared. The stationary charge is a negative 2 coulombs, so I'll put that in here. And the initial distance away from it is 0.13 meters, okay? So when I plug those numbers out, I end up with a negative 1.4 times 10 to the 11th volts. Volts. So that is my potential when this particle is here before it ever starts moving, right at the beginning of the situation, okay? So now what I need to do is I know that it's all potential energy, and part of it is going to get converted to kinetic energy because it's going to start accelerating in this direction. So how much potential energy is it going to have when it gets out here? Well, to find the potential energy out here, I've got to find the electric potential at that point. So the electric potential at the final position, again, KQ over R. And so K is the same. The Q is the same because it's the same charge that's making the field. And now it's going to be 0.95 meters away from where it was before, okay, or from the stationary charge. And so when I plug those numbers in and crunch them all out, I get negative 1.9 times 10 to the 10th volts. Okay, so now I've got an initial V and I've got a final V, so that means that I can then find a change in V. Well, just like before, change in V equals V sub F minus V sub I, and these are capital V's because it's not velocity here. These are capital V's. So my final velocity was negative 1.9 times 10 to the 10th volts. And I'm going to subtract the initial velocity from that, negative 1.4 times 10 to the 11th volts. And when I do that subtraction, I end up with a positive 1.2 times 10 to the 11th volts. Okay, so it's going to have an increase in potential energy according to this, given the fact that that was, an increase in potential, not an increase in potential energy. I've not calculated potential energy yet. So that's my change in V is positive. So now I can find my change in potential energy. Change in potential energy is Q times delta V. The Q, the movable charge, is a negative charge, so it's negative 15.1 millicoulombs. And so when I put that in correct scientific notation, it becomes negative 1.51 times 10 to the minus 2 coulombs. Okay, again in proper scientific notation. And I've got to put that with the 1.2 times 10 to the 11th volts. Okay, so multiplying those out gives me a negative potential energy, and I end up there with negative 1.8 times 10 to the 9th, not volts, joules. Negative 1.8 times 10 to the 9th joules. Potential energy is negative. Is that what I would have expected? Yes, because it's repelling, it's going that way, so kinetic energy is increasing. If kinetic energy is increasing, then I expect a corresponding decrease in potential energy. Okay, so now that I know what the change in potential energy was, if I know I'm going to have a decrease in potential energy, that corresponds to an increase in kinetic energy. Kinetic energy is calculated just like I've always done it before, 1/2 mv squared. So that hasn't changed at all. It's a decrease in potential energy, so I'm going to have an increase in kinetic energy. So this number is now going to be positive. So you've got to think through this and make sure that you got your signs right. So 1.8 times 10 to the 9th joules times 1/2 times the mass was 2.34 kilograms. There's a decimal point in there. Times V squared. And when I solve for V, I end up with 3.9 times 10 to the 4th meters per second as my final velocity at that particular point, okay? Now, does that look long? Yes. Does it look like the long problems that we did back in chapter 8 with the roller coasters? Yeah, it probably does. It looks just as long. But again, if you think through the steps, even though you have to do a lot of calculations, the steps follow a very logical thought. In order to calculate the change in potential energy of this particle, you have to know the change in electric potential. And you can calculate the electric potential because you know where this particle started, and you know where it's going to, well, it's not going to stop there, but this is the second position that we're looking at. So from its initial position to its final position, I can calculate the electric potential at each point. Then when I calculate the change in those two, I can go from potential energy, and then I can go to kinetic energy from there. So we're going to let you guys get some practice on that. I was also going to mention the first part of example 14.4 is basically exactly the same, and so I'm not going to work through that one. We're only going to go as far as the first part of the example of 14.4 for right now, and I'll let you get some practice with those problems, and then we'll come back in a day or two and we'll look at the second part of example 14.4.